Yes, just check and tell me whether the screen is visible.
Yes, sir.
Okay, so in the last lecture we were discussing about the implementation of stack. We had seen the stack implementation statically with help of array, and we also discussed its implementation program. Unfortunately, the recording didn't go well on that day, so I again had shared one video which was pre-recorded by me for the same concept, and I had uploaded that video as part of the recording is concerned uh, on on that day. And there was a missing portion of the dynamic which some students told me, sir, it was missing from the video. Yes, it was missing, so quickly we'll revise that before we move ahead with the next article. So as we were discussing, in case of stack implementation in a dynamic way with help of linked list, so if we are implementing a stack with help of linked list, the operation for push, the operation for push can be simulated with help of which operation? It can be simulated with help of create at start. The operation for pop can be simulated with which operation? It can be simulated with help of delete at start. It can be simulated with help of delete at start. Then traverse will be normal traverse, right? Traverse is our normal traverse of the linked list. And we also have top of stack, in which just we will print the data of the first element. We'll print the data of first element. So this is how we are going to code this stack using linked list. Now while doing so we are going to make use of relevant keywords from our linked list. We are going to replace the relevant keywords of linked list program with the stack program. Okay, so how I declare that? I declare struct stack, and inside that we declare in data, and we declare struct stack pointer to the next node, and we will be type defing this struct stack to a capital stack now, and we will be creating one external reference pointer called as top. We'll be creating one external reference pointer called as top. So the start gets replaced by top now in this case. Start gets replaced by top in this case, right? Then we have our main function. In main function, we'll be taking choice from the user, and we will be creating a menu driven program. We will be creating a menu driven program. So first choice will be push, second choice will be pop, third choice will be top of stack, fourth choice will be traverse, and fifth choice will be exit. Then we will be scanning the choice, and we will be creating a switch case for that choice, where for each case now we will be having our relevant logics. So we will have case 1, case 2, case 3, case 4 as our 4 logics, and case 5 will be exit for break. And we'll be writing one default case telling our user that this is an incorrect choice. Incorrect choice. So this is our normal structure of a menu driven program, and this do while loop will continue while the choice is not becoming 5 now, while the choice is not becoming 5, because 5 is our exit. Then we have push operation, right? So I write push function. First I write push function. So how I write push? This push is nothing but, what is this push? This push is nothing but our create at start. This is nothing but our create at start, right? So what we do in create at start? First we do a malloc. First we do a malloc, right? P is equal to node pointer. So here we'll be doing stack pointer, right? P is equal to node pointer means here it is stack pointer. Then we'll allocate the memory for that stack node. We'll be allocating the memory for that stack node. Then asking user to enter the data element in stack. and this data element will be scanning in piece data. This data element will be scanning in piece data. Correct? Then we will check. What is the condition that we check? If top is equal to null, because now start is get replaced by top. Okay. If top is equal to null means linked list is empty. Correct? And when linked list is empty, what code we write? Piece next is null and start is p. So here top is p now. Piece next is null and start is equal to p. This is what we used to write in singly linked list, right? Now here start is getting replaced by top, so top is equal to p. Else part, when linked list is containing some element, so in that case we write two statements. Piece next is existing start, so here start is top, so piece next is top and then top is p. Piece next is top and top is p. This is how we do a push. This is how we do a push. So from here the push will get called. Now let us quickly also code the logic for traverse. I'll just push this logic below main. So I declare those functions here. This is void push, then void pop. Let us do traverse first. Traverse. Okay. Then void traverse. Then in traverse, what we do? In traverse also we check whether the linked list is empty or linked list is containing some elements. If linked list is containing some elements, then only we go for printing those elements, right? So how we check whether the linked list is empty? So if top is equal to null, then linked list will be empty. So what is meaning of linked list is empty here? In this case now the stack is empty. Linked list is nothing but our stack. So here we'll print stack is empty. Try to use meaningful keywords now related to stack, because this linked list we are using to simulate the operations of stack now, right? Now if linked list is containing some elements, then we start moving in the stack. So initially q is equal to top, while q is not equal to null, we keep on jumping and printing the q's data. So percentage d, and we'll print the data every time on a new line. Correct? And after printing, we jump by writing q is equal to q's next. Q is equal to q's next. Are you getting this? So this is how we print the data using the traverse operation. So quickly try to save this linked list stack. And I'll just call the traverse. I forgot to call the traverse here. Just call the traverse. Okay, I forgot to include stdlib. So let us execute this now. So we have our 5 options: push, pop, top of stack and traverse. So we are performing push. We are pushing 10. Then again we perform push. We push 20. Then again we perform push 30, and then we traverse. Some mistake has been done. Wait, related to ampersand. Yes, ampersand. Push 10, push 20, and push 30. See 30, 20, 10 we can see, which is the ideal way of printing. Now 30 is at the top for us in that stack, right? Did you understand how we are simulating now this linked list with help of stack operations? One operation I have shown you, push. Did you understand? Some students had asked me this, sir. We were not able to see that part in the video. That's why I thought of repeating that part today, so that in today's recording it will be available for you. And if you have any doubt now, you can continue. Can you try pop on your own? Pop top of stack and pop operations. Yes, students.
Yes, sir.
Yes,
Or,
sir.
or do you want me to do it that pop and top of? You have understood, right? Pop is nothing but delete at start. Pop is nothing but delete at start. And traverse is nothing but you have to just print the tops data. So if I ask you to do a traverse here, in this case, what you need to print here is 30. So how I will print this 30? Simply I'll check whether the linked list is empty first. If linked list is empty, then top of stack is not there, right? So that condition how we will check? If top is equal to null, then then stack is empty, we will print. Otherwise we will print tops data. Otherwise we'll print tops data. Are you getting this? And pop is nothing but delete at start. Pop is nothing but delete at start. Now what we should closely observe here is, see, when we did push operation here, we don't have a phenomenon of overflow. We don't have a phenomenon of overflow. Why? Because if you remember, this linked list is a dynamic data structure. So here the size is not fixed. And if the size is not fixed, there will be no condition for overflow. When overflow used to happen in static implementation, when your entire stack was getting full. So if you declare the stack of size 5, and if you have 5 elements in your stack, and the moment again you try to do a push operation, then an overflow used to happen. But now that situation will not occur when you are doing stack using linked list, because in linked list we all know that this data structure is a dynamic data structure. In this, the size of data structure is not fixed. So as and when you require to add a new element in that data structure, you simply go for the create operation. You simply go for that create operation, right? And you allocate the memory as per your requirement. And you allocate the memory as per your requirement. Are you getting this? Okay, so there is no stack overflow phenomenon here in this case. There is no stack overflow phenomenon in this case. But on the contrary, stack underflow will be there for the pop operation. Let us do it. Let us not leave it. Okay, let us do that pop operation. So if we have void pop, here we will be calling the pop function. Here we'll be calling the pop function. Okay, and we will be having void pop. So if now our linked list, or say our stack, is empty, how we will check? If top is equal to null, then now linked list is empty. Indirectly our stack is empty. And if stack is empty and user is still trying to perform stack removal operation, then what phenomenon happens? Stack underflow. What phenomenon happens? Stack underflow. Stack underflow. Are you getting this now? Did you understand why stack overflow is not there and why stack underflow is there in case of linked list implementation? Any doubts, student? Okay, now if stack underflow is there, what is the else part? Else part is linked list is not empty. Else part is linked list is not empty. Right? And now in this case, delete can be performed. In this case, delete can be. Which delete it is? It is delete at start. Delete at start with linked list is containing some elements. Now, can anyone tell me what will happen here? Yes. Can anyone tell me what will happen here in the else part?
P is equals to top. Top is equals to top next. Printf delete stack is percent d p data free p.
One at a time. So what is the first statement that you wish to execute? P is equal to top.
P is equals to top.
So you wish to delete the first node. That's why the first node, which is nothing but top, now you are labeling it as P, correct? Then what next?
Top is equals to top next.
Okay, top is equal to tops next. Okay, then
Printf deleted stack is percent d p data, comma p
okay,
data.
so percentage D is popped, something of this sort, right? So we are popping that element, which is nothing but P's data, correct? Okay,
Yes,
what next? What next?
free p.
Free P. Now, if you have only one element remaining in your stack, whether this logic works well, what will happen? P is equal to top, correct? Top is equal to top next means top will become null in that case, right?
Null.
Correct. So, and we'll print P's data. So that will be the last remaining nodes data, right? And free P. So it works well. So only two cases are sufficient, right? So let us compile this now and try to execute. So I push couple of elements. So I have pushed two elements. You can see there are two elements right now, 20 and 10. And we do a pop now. So what it prints? It prints 20 is popped. It prints 20 is popped. So it is executing properly, right? And again, if we pop, then 10 is popped. 10 is popped. Again, now if I do pop, then stack underflow. Stack underflow. Clear, students? So likewise, the only operation that remains now is top of stack, TOS. Let us quickly do that also, so that nothing is left incomplete. So void top of stack, void top of stack. Okay. So in top of stack, as I told you, TOS. Okay. First, we have to check whether the linked list is empty. Means whether our stack is empty. In that case, we will write a printf statement that stack is empty, because there will be no top of stack when the stack is empty, correct? Otherwise, if stack is not empty, in that case we'll just write a printf statement that top of stack is percentage d. And what is that percentage d? It is tops data. It will be tops data. Simply we have to print tops data. You will not do any change to your top in this case, correct? Here we used to change. In case of pop, we used to write some logic here, right? Like this. We used to actually delete that, but that will not be there in case of TOS. In TOS, just we will print tops data. Just we will print tops data. So we'll compile and run this one also. So I push two elements, 10 and 20. Correct. So now which element is there on top of stack? 20 is there on top of stack, right? So if I do top of stack, it prints me top of stack is 20. If I pop both the elements, and again if I do top of stack, it prints me stack is empty. Prints me stack is empty. Is it clear? So this is how we implement a stack using linked list. So this was nothing but stack using linked list. Is it clear, students? Any doubts? Is the program understood to all of you? Stack using linked list?
Yes, sir.
Okay. Shall we move ahead with the next topic now? Okay,
Yes,
now
sir.
in stack we have few applications to be discussed. Okay, there are few applications of stack, but before I discuss those application, we will discuss the other data structure from this particular chapter. If you remember that name of this chapter given is stack and queue, right? So let us discuss both the data structures first, that is stack and queue, and after that we will be discussing their applications. So still we have one more point from stack, that is application of stack, but that we will be discussing after we learn the queue data structure, so that it will be easy for us to compare both and determine relevant applications. Okay, so I will keep a pause on the applications of stack right now. First we will discuss about queue data structure, and once we complete queue data structure we will discuss applications of both, that is stack and queue. Okay, so today we are going to discuss now another data structure, that is queue. Today we are going to discuss another data structure now from our chapter, that is queue. That is queue. Okay, now what is queue data structure? Now queue data structure is also a linear data structure. Queue data structure is also a linear data structure. What is linear data structure? You all know. Linear data structure means in this data structure also the elements will be organized in sequential manner or in linear manner. So the elements will be arranged one after the other. The elements will be arranged one after the other. Now in case of stack, if you remember, the one end was fixed. Correct? In case of stack, one end was fixed and the other end was being used for performing the insert and delete operations. Correct? One end was always kept fixed. We were not doing any changes to that one end. Correct? But in case of queue now, we will be having two ends. Like stack also. In stack also there were two ends, but one end we were always keeping that end as fixed. We were not changing. The only end that we were changing was the other end, and for that we used one variable called as top in our program, right? Now in case of queue we have two ends. We call those two ends as front and rear. We call those two ends as front and rear, and both these ends are operational now. Both these ends are operational. Now it is not like stack. In stack one of the end was fixed. One of the end was fixed. Here now both the ends are operational. And what are name of those ends? Front and rear. What is meaning of front? Front means पुढची बाजू असं आपण म्हणतो मराठीत. Front means the one which is standing in front. You can visualize in that way. Rear, what is meaning of rear? Rear means backside. What is meaning of rear? मागची बाजू. Rear means backside, right? So these two, front and rear, are the two ends of our queue. Now I will give you an example to make you understand the concept of queue. Now whenever we try to pay fees in our college, right? We stand in a queue. We stand in a queue, right? So one student is standing, then new student comes, he will be standing behind that, then third student will come, he will be standing behind that, and so on, right? So suppose 5 students are standing. So we have two ends now. The one who has come first is standing on which end now? Front end. He is standing on which end now? Front end. And the new students who are coming and standing in line, they are getting added from which end now? Rear end, means backside. Are you getting this? Okay, so these are our two ends, front and rear. These are our two ends, front and rear. Are you able to visualize that? Okay, so queue means any kind of queue that we have. Whenever we go to watch movies also, right? We stand in the line to take tickets. Correct. So front end is something which is at the front position, right? So from there, the people will get services and they will get removed from the queue. They will be getting removed from the queue. And if someone new is coming in the queue, from which end that element will be coming or that person will be coming? He will be coming from backside. So rear. So here both the ends are operational. Here both the ends are operational, right? So there again are two operations as like stack. One will be insert operation and one will be delete operation on our queue, right? Inserting operation will be carried out from which end? Inserting operation will be carried out from rear end. As I told you in the example just now, the person who is coming now to pay fees, he comes and stands at the back. Magna yeto to, right? He comes and stands at the back. So which end it is? It is rear end, back side. Correct. So for insert, which end we are going to use? For insert, we are going to use rear end. Similarly, if a person has already paid the fees after standing in the line, right? Then he is supposed to get deleted from the queue, right? So this delete will be happening from which end now? This delete will be happening from front end now. This delete operation will be happening from front end now. Did you understand now? Both the ends are operational. It is not like stack where insert and delete both were getting happened from the same end. Same end we were using for inserting also and for deleting, and other end was always kept fixed. But that is not the case with queue now. In queue, both the ends, rear and front, are operational. For inserting, the end used is rear. For deleting, the end used is front. The operation for inserting the element from rear end is called as enqueue. The operation for inserting the element from rear end is called as enqueue, whereas the operation for deleting the element from the front end is called as dequeue. The operation for deleting the element from the front end is called as dequeue. Like we call the operations as push and pop in case of stack. What are the operations called in queue? Inserting is called as enqueue and deleting is called as dequeue. Okay, inserting is called as enqueue and it is compulsory going to happen from which end? Rear end. And delete operation is called as dequeue. It is going to happen from which end? Front end. It is going to happen from front end. Now again, like stack, this queue will also have two type of implementation. Like stack, this queue will also have two type of implementation. This queue will also have two type of implementation. First will be static. This static will be with help of an array. Second is dynamic. Second is dynamic, and this dynamic will be like linked list, with help of linked list. So two implementations are there, unlike like the stack also, right? So static implementation with help of array and dynamic implementation with help of linked list. Now we had two phenomenon, if you remember, stack overflow and stack underflow. Those two phenomenons will also be there in your queue. So there is something called as queue overflow. There is something called as queue overflow and queue underflow. Queue underflow. What was stack overflow? Stack overflow was a situation in which stack was full and user was doing push. So what will be queue overflow? Queue is full and user is trying to do enqueue. Correct? Enqueue is nothing but insert, right? So if queue is full, if your queue is full and user is trying to perform which operation? Enqueue operation, and user is trying to perform enqueue operation, then it leads to queue overflow. It leads to queue overflow. Similarly, what will be queue underflow? What will be queue underflow? Queue is empty. Queue is empty and user is trying to perform dequeue operation. And user is trying to perform dequeue operation. then it leads to phenomenon called as queue underflow. It leads to a phenomenon called as queue underflow. Did you understand the basic terminologies in the queue data structure? Is it clear? Is it clear, student?
Sir.
Okay, so insert operation using rear end called as NQ, delete operation using front end called as DQ, two implementations, static with help of array, dynamic with help of linked list, and two phenomenon, overflow and underflow. Overflow related to NQ and underflow related to DQ. Now let us first discuss the static implementation by taking relevant examples and then the dynamic implementation, right? So first let us discuss the static implementation of queue by taking examples. Okay, so static implementation of queue, and this we are going to do with help of array. And as this is static implementation, we all know now the size will be fixed. So I take now size as 5. I take the size as 5. I take the size as 5. So suppose now this is my array of size 5. This is my array of size 5. Okay, this is my 0th index, first index, second index, third index, and fourth index. These are my 5 index. Are you getting this? Are you getting this, my dear students? Okay, now if I ask you to do NQ, see, I will tell you how this NQ will execute now. Okay, so if I do NQ 10, NQ 10 will be happening here. Correct? Next NQ, if I ask you to do, it will be happening here. Again NQ, it will be happening here. Again NQ is happening here. Again NQ, it is happening here. Again NQ, what will happen? What will happen if I do again NQ?
Overflow.
Correct. Okay, correct. So if I do again NQ, it will be overflow. Why overflow? Because queue is full, size is full, and user is trying to perform NQ operation. It is queue overflow, right? Now if I ask you to do DQ, which element will be DQ'd? Which element will be DQ'd?
50.
Imagine. So roll number 1, 2, 3, 4, 5 has come. Who came at the last? Who came at the last? 50. So will 50 will be allowed to pay fees first, or 10 will be allowed?
50.
10.
10.
50. If you allow 50 to pay fees first, then 10 student will create a problem in the line, right? Late येऊन सुद्धा त्याला कशी पहिला fee भरायला दिली. This is what he will tell, right? See, 10 out of these 5 elements, which element I inserted first? 10, right? Then I inserted 20. Then I inserted 30. Then I inserted 40. And then I inserted 50. Correct? So the elements were getting added like this. They were getting added like this. So imagine this as your rear part. Are you getting this? So he was coming and standing here. 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 And now, if someone wants to get deleted, from which end he will get deleted? So from front end, right? So this is something which is front end. Now, can you tell me which element will be deleted now? 10 will be deleted now.
10.
Correct. 10 will be deleted now, right? So this is a queue. So in queue, the one who will come first will get first service, right? In any queue for that matter, wherever we have queues. Correct. Queue is nothing but line, right? So in जो line में पहला आ गया उसको first service मिलेगा, right? The one who comes first in the queue will get first service. First come first serve, right? So in other words, this data structure is also called as FIFO. This data structure is also called as FIFO. FIFO stands for first in, first out. First in, first out data structure. The one who comes first will get out first. He will be getting service first and he will be getting removed also first. It is not like stack. In stack, what was happening? LIFO, last in, first out. So if you say 50 as answer, you are actually thinking of a stack. So if I rotate this diagram in an anti-clockwise direction for 90 degrees, it will look like this, right? Right? 10, then 20, then 30, and then 40, and then 50. And some of you were telling, sir, 50 will get removed. So if 50 gets removed, then it is like using the same end. It is like using the same end, which is nothing but stack. And which is LIFO. But now in queue, this is the end which you use for inserting. And this is the end which you use for removing the elements. Both the ends are operational. And that's why this data structure is called as FIFO data structure. That's why this data structure is called as FIFO data structure. FIFO stands for first in, first out data structure. FIFO stands for first in, first out data structure. Did you understand now the basic concept of queue? Now we need to take some examples before we actually implement this with help of queue, statically with help of array. Okay. So initially we don't have any elements. So initially our queue is empty. And we all know that there are two ends that has to be maintained. Which are those two ends? Front and rear. Which are the two ends? Front and rear. Now in static implementation of queue using array, initially we keep both front and rear to -1, which indicates us that our queue is empty. Which indicates us that our queue is empty. Like in case of stack, if you remember, there was one end always fixed. It was not changing. So we required to change only one end, and that handling we were doing with help of only one single variable called as top. And initially we used to keep that top to -1 to make us understand that the stack was empty. But in case of queue now, both the ends are operational. Both the ends can change their value. So we are taking two variables for those two ends in the form of front and rear. So this front and rear are our two variables, int front and int rear. Initially, both of these are initialized to -1. Both of them are initialized to -1, which helps us to indicate that this queue is empty. Are you getting this? Now, as and when we start doing operations of NQ and DQ, the values of front and rear are going to change and the elements are going to get scanned. Okay, for that we need to take examples. So we are just falling short of time for today's lecture. So I will pause our lecture today over here only. So taking those examples, we will continue in Wednesday's lecture. So as of now, what things we have discussed, because if I start taking examples, it will take a lot of time. So I am stopping right now today because I don't want to keep it half so that it will cause confusion for you people. So today only keep this thing in mind that now Q is another data structure, which is a linear data structure. Okay. Here also we'll have insert and delete, which are called as NQ and DQ. Here we have two ends. front and rear. Meaning of rear is backside. So inserting will happen from backside, that is from rear end, and deleting will happen from front side, that is front end. Okay. This data structure is FIFO in nature. FIFO stands for first in, first out. The one who will come first will get service first and will get removed first. Two implementation, static and dynamic, with help of array and linked list respectively. Two phenomenon, overflow and underflow. Overflow related to NQ operation and underflow related to DQ operation. First, we have started with static implementation of queue using array. In that, we have taken an array of size 5. So we can store maximum 5 elements in that queue. And in order to maintain both the ends, we are taking now two variables, front and rear. Initially, both these variables are kept to -1, which indicates us that our queue is empty. On Wednesday's lecture, I'll take more examples to help you understand how actually this NQ will happen and how the values of front and rear will get changed whenever you go for NQ and DQ operations. And then we'll write relevant logic for static implementation of queue using array. Is it clear? So we'll stop for today's lecture, but before that, let me take your attendance.